way it is, electronic parts, mostly very, very rigid things. You need a controller for them to be computed, to be programmed. You need sensors actually, so that they're safe to work with everybody in the company. They need sensors to not harm anything around them, and they need sensors to actually be able to handle parts and more fragile parts. And this is in complete contrast to, for example, biological systems, where we don't really need to have a huge computational power to actually be able to move up and down these stairs here, because if I start thinking about it, I would trip. And biology and nature uses actually something very cool, which is morphological computation. So by design, I am able to move my leg that way, and at many different angles, because I would break something. But we have like a rigid inner part, we have muscles, we have tendons that move in a certain degree of freedom, and we don't need to really think about it because we have implanted these ideas here. And the cool part is you can also do it with completely flexible systems, like this little octopus here, who's able to actually grab a very hard shell, take it away, run over a run or crawl over a very compliant surface here, sand, and can dig away and even come to another place, and maybe even build this little home here, also very compliant. He's completely, the only hard part here is his beak. And you can see he can even hide himself here. So it's very nice and high flexibility, and that's what we use in soft robotics, because there we have a complete soft system based on soft materials like silicones or even 3D printable GPU parts. It started with curing these things. So we used silicons back in the day. We would cure them, we would build them, and then we get like distributed actuators all over the body. So we can actually make those then move in different ways. We have multiple degrees of freedom here, and we use one of the main things that we use is pneumatics. So we have a compliant body that is actually pressurized with air. When you see these air chambers here in unpressurized, they normally just like flat, and then they bend into the direction of the smaller stiff parts here, and that you can use them then to do interesting things. And with modern technology, you can really also 3D print all these things and make, for example, self-adaptive grippers. Like you can see here, this is a fully 3D printed gripper, 3-finger gripper, and what's cool is when you can inflate it, you can grasp an object. Here we have a can full of Coke. And the cool part is it actually configures itself to the object. So it can hold it, it doesn't squeeze it, doesn't crush it, and if you even increase it, it would bend away again and keep the full compliance. So it's really, really safe to use in, for example, human-machine interaction, and you don't break fragile parts. As I said, I do bio-inspired things and use bio-inspiration not only from animals but also from plants. So we also do carnivorous plant-inspired systems. They're soft robots, hard robots, for example, an artificial human flight track gripper. And I have a workshop in the afternoon, so if you want to see that thing and play with it, you can see how we printed it. And we also do medical devices that are 3D printed that can save lives with the trick of nature. Here the very fast snapping motion, closure motion of the bladderwort. It's actually quite interesting because that is the fastest plant motion on the planet. It takes 50 milliseconds to open and close its trapdoor. If you want to see that, I can show you slides later in the workshop. And we do animal-inspired systems. So we look into nature and say, okay, there's, for example, the tendon locking mechanism of birds. That's the reason why they actually don't fall off trees, because they lock the tendons when they grasp, and they can sleep with that and don't fall off, but they really need to learn how to reopen that. Again, we transferred that to a fully 3D printed gripper system, and also we built insect-inspired 6-legged robots with compliant parts, and our fully 3D printed electronic-free soft robot that actually can walk just by an input of air. And I'm going to tell you a bit more about why we actually built electronic-free systems, because we want to implement all of these controls into one system. We don't want to have a complex control system, because when we did start with all of these pneumatics things, we really needed check valves, we needed a compressor, we needed a microcontroller to control the motion of our robots. And we thought, okay, that is stupid because nature does it in one pack. And then we thought, okay, how could we translate, for example, the motion of the leg of this little tortoise here? And we thought, why don't we do electronic free control systems and add pneumatic logics into these? And the robot here can actually do the same movement as the turtle, forward, backward, and downward motion of the legs. And we could then introduce a, for example, trot gate using our electronic free logics here, which we 3D print fully and can make not an OR gate, create not an OR gates and control circuits with that. So we have and we enable with that complex motion without a complex control. And why I'm here today is because we use pusher printers to actually build these, and these were the only very precise systems that we needed to actually build that with a very, very flexible material. The Filaflex A70 here, and that enabled us to make bendable round 1mm channels. And when we put them in between two pneumatic cushions, we actually can squeeze them shut and then not have a signal running through the green tube here, and then we can create ones and zeros and have all analog logic. And as we can 3D print them, you see one of our logic gates, we can also play a bit with them and see how robust they are. And the cool part is you can actually squeeze them down to 2mm and they can still function afterwards. So through the TPU material that we use here, we have an extremely robust system, and then we can 3D print our robots from that and use them in environments that are quite extreme and they will not break. And when I say 3D print them, if you want to have one of those for your home, you can actually 3D print them in 50 hours, scan the code here, it's on printables, and you can see if you can print these at home and have a little toy with you, or we can do a bit more with these. We can put them under pressure and then we can let them walk around. You can even step on them and they will not break. I will have them, but I will let that walk again in the workshop later. You can put them actually underwater and they can transport things. They can interact with the environment there. You can even run them over with your car, and that is the one we ran over with the car. You can throw them off a building, so you can really use them in environments that are dangerous to different hard robots, or use them, for example, with these electronic-free controls in environments where electronics would fail, like high radiated or high magnetic things. But you can see it only runs in one direction, and we wanted to use them to be able to interact with the environment. So we needed to answer the question, how can we now sense an obstacle with only using pneumatics and a 3D printed part, for example. We thought, okay, we take a step back, look at our bigger system, because we have your breadboard robot, where we just can configure different logic gates together and 3D print parts that we need. And we actually added a contact sensor on the front, then added a pattern adjuster on top, have a motion switch. We have a 1-bit storage here, so we have actually memory in the system. And the soft sensor is quite easy to 3D print the full part. You have, in general, you have just a king tube that is in a PLA setting, and when you push it down, it opens the king tube. The robot is happy, it knows now, oh, I hit something, and I can walk away again. So with that, we can actually make now autonomous robots that are able to interact with the environment or actually recognize the environment. And on the right side, you're going to see a tethered version of our 6-legged robot, and on the left side, you're going to see a untethered version where we have the two